So hi and hello there, welcome to the new video of the course, and in this particular video we are going to see that, or basically we are going to understand that why the voltage divider bias is also known as self-biasing circuit. Okay, so we will understand this particular concept, that why the voltage divider biasing technique, voltage why the voltage divider biasing technique why the voltage divider biasing technique is also known as self-biasing technique, or the self-biasing circuit is also known as self-biasing circuit. Self-biasing circuit. So we are going to see this particular thing in depth. Okay, so for that we have to assume certain things. So as you can see over here, this is the circuit for the voltage divider bias we had seen in the previous session, right? So now let's suppose this is the current I1 flowing through the resistor R1. Great. Okay, and now as soon as this current is going to reach over here, obviously it would be getting divided into two parts. So the very first part would be I2 would be flowing through the resistor R2, right? And then the other part would be IB, that is a input current flowing through the base terminal. Okay, flowing through the base region, or flowing through the base terminal. Okay, so I hope you understood this thing up till here. So now what we will do, by applying KCL by applying KCL or Kirchhoff's current law, what we will get is this. See over here, I will take blue one only. I1 is the incoming current, whereas IB and I2, they are the outgoing current. So how we are supposed to write this particular equation? We are supposed to write this particular equation in this way, that is I1, just a second, that is I1 is equivalent to IB plus what? IB plus I2. Okay, I1 is equivalent to IB plus I2. So I can also write this particular equation in this way, that is IB is equivalent to I1 minus of I2. Great. So let me just highlight this particular point, or this particular equation, because we will be using this particular equation for analyzing further things, right? So this is the most important thing you should remember. Okay, and we also know that which we had seen in the previous session, this particular equation, this one IB is equivalent to IE divided by 1 plus beta, right? So just a second, this was the equation. Let me just IB is equivalent to, let me just copy from here only. IB is equivalent to IE divided by 1 plus beta. Let me check if it is able to paste. Oh no, sorry. So I need to write it somewhere over here. So it should be IB is equivalent to IE divided by 1 plus beta. So this is the another equation you should remember, 1 plus beta, right? And let me just highlight this particular thing roughly only. I'll just highlight it roughly. Okay, so moving to the next page. So now we have to analyze this particular circuit in this way. See over here what we had done. We had assumed this three particular current, and the direction of this current are in this way, like I1 is moving downwards, or it is an incoming current for this particular node. On contrary, IB and I2, they are the outgoing current from this particular node. Okay, great. Now you may get confused over here. What I'm going to do, I'm again going to apply KVL in this particular direction. But now you will tell me that sir, over here, like in the previous session, when we assume that, like when we applied KVL, so we assume that the current I, which is flowing from the R1, the same amount of current is flowing from the resistance R2, right? From the resistor R2. But here you are showing that there are two different currents. There are two different currents flowing through this particular resistor R1 and R2. So there is one reason for it. As you can see over here, we are connecting this particular BJT, right? On contrary, over here, if you could remember, or if you could see very clearly, we assume that this particular terminal is open. Okay, we assume that there isn't any load or there isn't any BJT connected over here on this particular side. So that's why no current will flow over here, and thus the current I will move in the downward direction only. But here, since we are connecting the BJT over here in this particular circuit, as you can see, to the base like this particular plus VB to the base terminal of the BJT, so obviously this current is going to bifurcate from this particular node. Okay, and one current will flow to the base of the transistor, that is IB, right, and the another current will flow to the uh, resistor R2, that is I2, right. So what we'll do, applying KVL in this particular direction. Wait, I'll just sorry, I will just apply the, just show the direction. So in this particular direction, the KVL would be applied. So the KVL would be applied in this particular direction. So in this particular direction, the KVL is applied, right. So KVL is applied in this particular direction. So now we'll apply KVL. So it would be plus see over here, plus V minus of I1 R1 minus of I2 R2. Okay, so plus V minus of I1 R1, just a second, minus of I1 R1 minus of I2 R2, and that is equivalent to 0. Now what we'll do, we'll move this particular part to the RHS, and thus we will get this particular equation as V is equivalent to I1 R1 R1, right, minus of what, minus of I2 R2, right, minus of I2 R2, right. So now according to this particular equation, we can write I1 as IB plus I2. Great. So how we are supposed to write this particular equation? We are supposed to write this particular equation in this way, that is V is equivalent to I1 can be written as IB plus what, IB plus I2, right, IB plus I2 bracket close into R1 plus R1 minus of I2 R2, right, minus of I2 R2. Great. Then we need to multiply this particular currents with this particular resistor R1. Okay, so it may take different color, so it would be like V would be equivalent to IB R1, right, IB into R1 plus I2 into R2, I2 into R1 minus of what, minus of I2 into R2. Great. Minus of I2 into R2. Now if you could see very clearly, just a second, what I will do, I'll just take this particular thing as common. So our V would be equivalent to IB R1 plus rather I will it as plus I2 to bracket R1 minus of R2. Just forget this particular point as of now. This is not that important. What is important is this. See how I'm supposed to write this particular thing, that is IB. IB. I can write it in this way, that is IB is equivalent to IE divided by 1 plus beta. Great. So IB can also be written as IE divided by 1 plus beta bracket complete into R1. This is your voltage V, and this is the current I2 plus I2 R1 minus of R2, right. Great. So now if I move this particular thing, that is this particular thing, see over here, this one to the LHS side, it would be getting subtracted, right. So what, so let me just copy this particular equation as it is, so that it would be easier for us to solve this particular thing. Let me just copy this particular thing properly. Just a second. I hope you understood everything up till here, right. So Control C and Control V. Let me move it little above. Great. So now what I am going to do over here is this. That means what? I2 into bracket R1 minus R2, R1 minus of R2 is equivalent to what? Is equivalent to V minus of IE, V minus of IE divided by 1 plus beta bracket complete. Okay, bracket complete. It is multiplied with R1. It is multiplied with R1. Okay, so this is the main equation, right? With the help of this particular equation, we can easily say that voltage divider bias is also a self bias circuit. Now you will ask me, sir, how come? Like, I'm not able to understand anything with the help of this particular equation. See over here, we all know that IC is almost equivalent to IE, right? So if IC increases, right? If IC increases, that means what? Your IE also increases, right? Your IE also increases. And we all know that IC increases only because of one factor, that is due to increase in external temperature, due to increase in external temperature. And if the external temperature increases, right, so your IC increases, and so your output so your emitter current IE also increases. Now if you look very clearly over here, if your IE is increasing, okay, it is if your IE is increasing, it is getting subtracted by this particular DC supply or the DC voltage, and thus whatever the value you would be getting for I2, it would be less. If you could see very clearly, if your IE is increasing, your I2 is decreasing at the same time, right? Now you will tell me, okay, that's fine, I understood this particular point as well, but what will happen if I2 is I2 is decreased? My dear student, see over here, if I2 is decreased, that means what? Your VB at this particular voltage, VB also decreases. Okay, that means what? If VB decreases, that means what? Your IB also decreases. Just a second, we'll obtain this relationship as well. Just a second, let me just clear all of these points. We'll write this, we'll try to understand this particular points theoretically. So I'll take this one. Oh, sorry, maybe this one. Yeah. So as IC increases due to increase in external temperature, and we had seen this particular relation in the previous session as well, that is IC is equivalent to beta times of IB when you are operating this particular BJT at the room temperature, right? But as soon as you are moving out from your room temperature, let's suppose the external temperature got increased, so there would be one more current, that would be ICBO, and that would be getting multiplied with this factor, that is current gain 1 plus beta. Okay, so this is the external so this is the extra current which you are getting. Okay, and due to this particular current, this value of IC is increasing, and this value of IC is increasing because of this particular temperature. Okay, because of this particular temperature, this current ICBO is getting introduced in this particular equation, and thus the overall value of the IC is increasing. So that is the main reason, right? We all know that IC is almost equivalent to IE, right? So just a second, as IE increases, right, as IE increases from the above equation, we can clearly see that the value of current I2 decreases. I'll directly write I2 decreases. As you can see very clearly. Well, as IE is increasing, okay, it is getting subtracted with this particular factor, and then due to this reason your I2 is decreasing. Okay, so I hope you are getting my point. Okay, so what? As IC, just a second, as I2 is decreasing, so your VB also decreases. As I2 is decreasing, as I2 decreases, as I2 decreases, VB also decreases, right? VB also decreases. And we all know that VBE, just a second, that means voltage between base and emitter terminal, it can be written as VBE is equivalent to VB minus of VE. Great. Okay, so now as you can see over here, VE can also be written as IE into RE. See over here. Oh, I think I had not drawn that particular RE resistor, but anyhow it is written over here, or it is drawn over here. So as you can see, there would be one current IE flowing in this particular direction, and this is your emitter voltage VE, right? So just a second, let me erase all of the thing. So VE can also be written as, just a second, IE into RE. Great, fabulous. We understood everything up till here, right? So as my IE is increasing, see over here, as my IE is increasing, so my VE will also increase. Okay, but on contrary, what we saw, as my IE was increasing, where it is, yeah, as my IE is increasing, I2 decreases. That means what? My VB also decreases. So as IE increases, VE increases, but my VB is decreasing. That means what? Your input voltage decreases, or VBE, overall voltage VBE decreases due to increase in output current IE. This is the most important conclusion. Just a second. IE or IC, it's up to you. You can write any of the thing, IE or IC, right? Is almost equivalent to IC, right? So this is the most important conclusion. Again, I will like to repeat this particular point. We derived this particular equation, okay, and as you can see over here, on basis of this particular equation, we concluded certain things. So as we all know, so as IC increases, that means if the output current increases, and how it is increasing, it is increasing due to temperature. Okay, as the external temperature is increasing, this particular value, that is ICBO, is getting introduced, or it is getting added with this particular thing, that is beta times IB, right? So thus it is increasing the overall output current, right? Overall value of the output current. Great. And we all know that IC is almost equivalent to I. Okay, and as IE is increasing, right? If IE increases, that means the emitter current increases. With the help of this particular equation, as you can see, if emitter is increasing, I mean the emitter current is increasing, this value increases, but it is getting subtracted with V, right? So that means what? Your I2 decreases. Okay, your I2 decreases. Great. So as I2 decreases, this VB also decreases. That means this particular voltage VB, right? This is the voltage VB. It also gets decreased. Okay, and now we all know that VBE can also be written as VB minus of VE, right? And we all know that VE is equivalent to IERE, and if IE is increasing, VE is also increasing. Thus, it is decreasing the base voltage, that is VB, and thus the base emitter voltage would be decreasing. So VB decreases due to increase in output current IE, and this is the most important conclusion, that as VBE decreases, IB also decreases, right? And what? And if IB decreases, and so IC also decreases, and IC also decreases. Why? Because we all know that IC is equivalent to beta times of IB. Great. So now you will tell me, how come, sir? How, like, what is the relationship between VBE and IB? My dear student, we had already we had already seen this particular relation. If this is your, just a second, if this is your VBE, this is your IB, remember the input characteristic of BJT? There we had plotted this particular graph. This was the graph for VB. Input characteristic of BJT between IB and VB. So as you can see, if my VB is increasing, so my IB is also increasing. If my VB is decreasing, right, so my IB is also decreasing. Okay, as you can see over here, this is the this is non-linear characteristic, but still, you like, just by looking at this particular graph, you get a clear-cut idea. And there we had actually written in the conclusion section that if the input current is increasing, sorry, if the input voltage is increasing, so the input current is also increasing. Okay, and if you could remember the output characteristic of BJT, just a second, let me draw it over here as well. So I hope now you are able to relate this particular concept in depth. So it was something like this. I'm drawing with my rough hand, I'm drawing it roughly. So these were the different set of values for IB. So this was IB1, this was IB2, this was IB3, right? And with respect to this IB, there were certain values of IC as well. So this is IC1, this is IC2, and this is IC3. So as you can see, as my IB is increasing, so my IC is also increasing, right? So this was the most important thing, and obviously the gain would be beta, right? The amplifying factor between both of them was beta. So now I hope you understood that why it is known as self-biasing circuit. But still, I know that you might have one doubt in your mind, like why it is known as self-biasing. So my dear student, again I'm drawing this particular plot over here, or this particular graph over here. Just a second. Just a second. Let me draw this particular graph. That is the output characteristic of BJT. And let me just draw one rough load line over here, something like this. Just a second. I will take a rough load line, something like this, right? And I will just draw one rough graph, the output characteristic of BJT. Just a second. Something like this, right? It would be something like this. So let's suppose we had biased this particular transistor over here. That means this is the Q point of this particular transistor. So this is the Q point, that is IC and VC, IC and VC, right? Now what happens really is that due to heating your temperature, due to the, like as the external temperature increases, right? So your IC also increases. That means what? This Q point shifts somewhere over here. Like from here, it may jump somewhere over here, right? It may jump somewhere over here. So as you can see, there is a shift in a Q point, right? Due to external temperature. So this is what? This is the shift in Q point due to external temperature. Shifting of Q point due to external temperature, due to an external temperature, due to the external temperature, right? So due to the external temperature, this Q point gets shifted. Okay, why it is getting shifted? Because IC is increasing. Okay, why? Because I'll write over here in the bracket, IC increases, and as the IC is increasing, so as I just forgot to draw over here. So this is the IC versus VC plot. I hope you know this particular thing. I just forgot to just name it, but I hope you are getting my point, right? So as the IC is increasing, so obviously this Q point is shifting upwards due to the change in the external temperature. That means if the temperature is increasing, then obviously this current IC is going to increase, right? Output current IC is going to increase, and thus there would be a shift in Q point. But on contrary, what is going to happen? So as your Q point is moving above, or it is going to shift, I2 is decreasing, right? See, I hope you are able to imagine this particular thing. As your output current is increasing, at the same time this current I2 is decreasing, and as the current I2 is decreasing, what is really happening is that the base voltage, or the VB decreases. Okay, and we also know that V is equivalent to IERE. That means what? Your overall emitter voltage is increasing with decrement in the base voltage. Okay, and thus your VB, that means input voltage, decreases due to increase in the output current. That's the important thing that is happening. And as the VB decreases, so your IB also decreases, and this is the relationship between the VB and IB, which we had seen in the input characteristic of BJT. Okay, and now I hope you are able to understand this particular thing. And as VB decreases, so your Q point, again it is shifting over here. So again your Q point is able to come over here at this particular point from here to here, right? So change in a Q point due to, I'll write over here, just a second, yeah, somewhere over here. So basically Q point is change in a Q point, or what I'll write, refocusing of Q point or readjustment of Q point readjustment of readjustment of Q point is possible, or it is easily achievable due to this particular voltage divider bias, due to R2, okay, or what I can write, due to this particular designing of voltage divider bias, due to voltage divider bias, right, due to voltage divider bias technique. Right, I hope you are getting my point. Due to this resistor R2, or due to this particular uh, RE or R2, whatever I can say, it is able to achieve this particular, or it is able to regain this particular Q point, okay, or the location of the Q point, okay. So basically not R2 as such, R, yeah, R2. And basically what we can see over here is that, yeah, as your IB decreases, so our IC also decreases. So basically this is how the things are going to work, right? So I hope now you are able to understand this particular thing in great depth, okay. So due to all this reason, like, see, a Q point goes up and it comes back on its own, okay. So this is a self process, right? No one is doing externally. So basically with the help of voltage divider bias, this transistor or the BJT transistor is able to what I can say, readjust the Q point on its own, okay. So it is doing all of this process on its own, so that's why it is known as self, okay. And what exactly it is doing, it is achieving the bias point, okay, or the Q point or the bias point on its own. So that's why it is known as self bias technique, okay. So that's why this particular technique, or the voltage divider bias technique, is also known as self bias technique. Not only that, even the collector to base bias technique is also known as self bias technique, which we had seen in the previous session. So that's why I took this particular thing in just one slide, okay. So whenever you will refer my PDF, you will be able to know each and everything in depth. So as you can see over here, just a second, yeah, over here as well I had given the same explanation. So like the collector to base bias is also known as self bias technique, and this one as well, the voltage divider bias, is also known as, is also known as self bias technique, okay. And I hope that you understood the concept or the reason in depth, okay. So if you have any doubt, feel free to ask me at any time. I will surely help you throughout the course, okay. So I am ending this video over here. Thank you.